Okay, welcome everyone to our experimental math seminar. We are very glad to have Christian Bean today from the UK. He will tell us about a very appropriate topic, namely combinatorial exploration and permutation classes. Go ahead, Christian.
There you go. Thanks, Diane. So today topic is going to be on enumerative combinatorics, and in particular, we're going to be looking at permutations and permutation patterns. It's going to be sort of twofold, where we're going to have a brief mention of some of the history of some of the automated enumeration methods used in the field of permutation patterns, and then I'm going to quickly turn to the propaganda for my own methods and approaches. Um, just here, there we go. So we all know what counting is. It's just the act of determining the number of objects in a set. And obviously, combinatorics, sometimes we describe it as the mathematics of counting. So what we'll be counting is what we call combinatorial sets. So these are just sets of objects with a notion of size, where there are finitely many of each given size. And the question we ask is, how many are there of each size? So some examples that we're probably all familiar with. We have things like words, where the size is simply the number of letters in the word. That is paths. Graphs, it could be the number of vertices, and then partitions. And then the one that we'll spend most of our time on today is permutations. And so permutation simply is a bijection from a set to itself, although I tend to just think of them as an ordering of the integers 1 up to n, and where n is the size of the permutation. So in particular, we're going to be looking at permutation classes. So I'm going to define that properly now. For me, I actually tend to think of permutations as a collection of points. So here is a permutation. Now, how do I go from the points to the permutation? Well, if I just label my points from bottom to top, 1 through 8, and then I read these points from left to right, I read off permutation 4, 1, 2, 5, 7, 3, 6, 8. So this is what we call the plot of the permutation, where it's just a set of points I, pi, I for the permutation pi. We are interested in patterns. So what do I mean by a pattern containment? So we say that a pattern contains another permutation if it contains a subsequence, not necessarily consecutive, that is in the same relative order. So for example, our permutation here contains the permutation 1, 3, 2, which can be seen by looking at the subsequence 2, 7, 3, for example, since the 2 is the smallest, 7 is the largest, and 3 is in the middle. In other words, it's in the same relative order as 1, 3, 2. Or put otherwise, in this picture form, if I highlight the points of the 2, 7, 3, then we see those 3 points are in the same order as the 1, 3, 2 in the permutation, which is why I enjoy this pictorial view of my permutations. Okay, so this containment forms a partial order on the set of permutations. And so a permutation class is then simply a set of permutations that is closed downwards with respect to this partial order. So that is, if a permutation is in the permutation class, then every permutation that it contains is also in the permutation class. So a permutation class can be uniquely defined by the set of minimal permutations not in the set, which we often call the basis, which can sometimes be an odd terminology if you come from linear algebra or something, but that's become the name that we use in the field of permutation patterns. It's completely stuck, so we're going to have to keep going. For some notation, we write AV of B to be the set of permutations that avoid every permutation in some set B. And so the question that we're going to spend most of our time asking is, given some basis, how many permutations of each size are there in the permutation class? So if we just do a quick example, how many permutations are there that avoid the permutation 2, 1? Well, of course, if we think of that pictorially, that's telling me that my points must all appear in increasing order. So there must be exactly 1 of each size, namely the identity permutation. This 1 through n. Okay, so that's too easy. Let's move on to something a little bit harder. Let's consider size 3. It turns out for size 3 permutations, we get this nice theorem that says that every permutation class defined by avoiding a permutation of size 3 is counted by, well, the size n permutations are counted by the nth Catalan number. So if you're not familiar with the sequence, it's one of the most common sequence of numbers that appear, and whenever you see that, you know that you're onto something nice. But why is that? It'll take a little bit more convincing. So first, from our definition of pattern containment, it's going to be closed under the symmetries of the square. If you think about the picture with the points, like if I just rotate my square around and I rotate the pattern, then the containment order is maintained. So you can simply see that the symmetry of the squares will maintain this pattern containment. And so from this, if I think about that, it turns out there's only two real symmetry classes going on for the size 3 patterns. So let's think about the second one, AV132. So we'll just pick out one of the candidates, and the others are, of course, just a symmetry. So how does this work? So if we just imagine we take some permutation in this class of size n greater than 0, so some non-empty permutation, then it can be written as some alpha and beta, where alpha and beta must avoid 1, 3, 2. Or in my pictures, that looks a bit like this. I can isolate where is this maximum element, and I'll put these gray boxes to say that there's no points above that point. Okay, well then, what would an occurrence of 1, 3, 2 look like? Well, it must have the points are in this order, so this is something that must be forbidding. So that tells me then that all of the points to the left of the maximum must appear above and to the left of the points on the right. So we must have this picture here, where we have the alpha on the left above the beta on the right. And if you stare at this long enough and you think about the pattern 1, 3, 2, you can convince yourself that there's no way of creating a 1, 3, 2 crossing from the alpha to the beta. So this gives a full structural description of the non-empty permutation classes in AV132. And in particular, from there, we can write down a recurrence relation to count this by just saying, well, if I have some permutation of size n, then put k points in alpha, 1 point for n, and then the remaining n minus k minus 1 points goes for beta. And they must simply be another occurrence of Cn here. Okay, and so to those of us that are familiar, that is the Catalan recurrence. So we're already happy and we say this is counted by the Catalan numbers. If you want a little bit more convincing as to why that is the case, then I suggest you would use a generating function to do that. So if we take the same structural description, but instead translate that to a generating function equation, we end up getting this equation f of x is equal to 1 plus x times f of x squared. So we have this quadratic equation which we can simply solve, and we'll find that the generating function for this particular permutation class is given by this. Then if you apply the general binomial theorem, you can have you can quickly find this, if you wanted to, that this is counted by the Catalan numbers, that formula, that 1 over n plus 1 to n choose n on the previous slide. Okay, so that is my sort of whirlwind tour of permutation patterns and some of the counting techniques in enumerative combinatorics. So let's just pause, take a breath, and summarize by coming up with sort of a pipeline of how we're actually doing enumerative combinatorics. So how has it worked so far? What we were doing to start with is first we found the structural description, and from there we were using some symbolic combinatorics, using those methods from Flageolet and Cedric, for example, where we convert this into some system of equations on the generating functions, and from that system of equations we can use some algebraic methods. Often it's a little bit harder than the quadratic formula, but maybe it'd be like a Grobner basis or something to solve to find the generating function and get the exact enumeration. Or we can apply some analytic combinatorics perhaps and get some asymptotic estimates. So this is kind of the general path of how an enumerative combinatorics tends to do their job. However, I kind of fibbed a little bit because we don't usually start with structural description, right? We start up here, we start with the problem statement. We're interested in a combinatorial set. We first need to find the structural description ourselves. And that's where all the fun comes into it for us mathematicians. We want to now have these, we often have these very clever ad hoc methods for finding that structural description. So That is where we're going to primarily focus on today. We're going to try to automate that final step where we go from problem statement to structural description. We want to find a way to teach the computer how to reason with combinatorial sets to find these structural descriptions. Okay, so let's do this example one more time, but now I'm going to do it to you the way that our algorithm will do it by computer. Okay, so we're going to look at AV132 done by a computer. So this is the structural description that our algorithm would spit out for this particular permutation class. These objects are what we call tilings. Let me try to describe them. So inside each cell, we have these red permutations. They indicate things that must be avoided. And in some of these cells, we have these blue permutations. These indicate things which must be contained. And in the top there, we have that 1 by 1 with the 132. That's our root. That represents precisely the class of permutations that avoid 132. And the first thing in our argument was we said either the permutation is empty or it is not empty. So on the left, we have that empty box representing just simply the empty permutation. And on the right, we now have that blue point appear, meaning that we must now contain the permutation 1 also. And then we place the point. So now we have this sort of thought of decomposing it into looking like alpha and beta, where on the alpha we have some property in particular. We know it must avoid 132, and in the beta it must avoid 132 as well. So of course, when we place this point, all we really need to do is we just need to stretch that 132 from the tiling it came from in every possible way. And this is what, if you trust the computer, is every possible way that it can be done. Then we can simplify some of these instructions. So if we look, for example, at the instruction that starts in the bottom left corner and goes up to the middle top box with the point in it, and then back down to the bottom right corner, that's a 132 occurrence. But we know that point actually exists. That is the n. So in particular, we can reduce this instruction to just avoiding a 1, 2 across the two cells. Okay, so we no longer need to worry about that. So we simplified that. And then in this next tiling, where we have that 1, 2 crossing, observe that the other two crossing obstructions here, they also contain the crossing 1, 2. So in particular, since I'm already avoiding the smaller permutation, I can ignore the bigger permutation. So we can infer away those bigger permutations and we have just this simple picture. But this was the picture that we had when we were justifying to ourselves that we could separate the permutation. So since I'm now avoiding 1, 2 across those two cells, it follows that the left-hand side all appears above the right-hand side. So we end up getting this nice decomposition. We're now at the end here. After separating, I can simply factor this into the three outputs, the point, and then we're recursing back to the root itself. Okay. So we call this structural description, we'd call it a proof tree, or more formally, it is a combinatorial specification. So that is, it's a set of combinatorial rules using these admissible constructors. So here I've just used disjoint union and Cartesian product. We'll talk a bit more about admissible constructors a bit later. Well, except for maybe the point tiling where I've just said I know the answer there, which I think is a fair thing to do because we all know that that's just one of size 1. Okay. Okay, so this is how a computer kind of does this. So each of these branchings we call a rule, and each of those sort of blue boxes where I've pointed out what that rule was, we say it's a strategy that has been applied to create that rule. So these tilings, if I try to define these a little bit more precisely, a tiling is then just simply, well, it is a triple of where the first thing is the dimension, the second thing is going to be the set of obstructions, so these are the things to be avoided, and then the third thing, this R here, is going to be the what we call the requirements, and these are going to be things that need to be contained. And these are just all simply these permutations that we can draw on this grid. And note in particular, for example, that point here that can actually be represented by some obstructions and requirements, but just for a shorthand, we draw a point so that we see where the points are. So what this tiling really represents is the set of gridded permutations that can be drawn on the tiling without creating any of the obstructions, and making sure that we actually contain every requirement. And so, for example, if I take my box and I just draw some points until I definitely contain that blue 2, 1, but now make sure that I never accidentally create one of the red obstructions, this would be an example of a permutation that happens to be on this tiling. So here we see that this permutation 6423751 is a permutation on this tiling. Although strictly speaking, we should really be saying is a gridded permutation on this tiling, where the 6423 are in the first cell and so on. Okay, so this is my tiling objects, which allows me to reason with permutation patterns and some of our structural ideas in a very convenient way. So if we go back to our proof tree, one of the reasons why tilings are so useful is that not only does it allow us to reason with them, it also allows a computer to reason with them really easily. So here is a little code snippet. This is precisely this permutation, but written in our Python implementation of tilings, where here you can see now, if you look at the first obstruction there on line 5, it's the gridded permutation 0, 1. Unfortunately, I've moved to Python based, so now things are 0 based, so apologies to the mathematician. We're now looking at our permutations as 0 based permutations. So we have this crossing obstruction 0, 1 that starts in the cell 0, 0 and goes to the cell 2, 0, for example. And if you look there, every permutation, or each of these gridded permutations can be represented in code very straightforwardly. So we get this tiling. And moreover, we can then implement each of these strategies in our code as well. And then if I want, I can apply the strategy to a tiling, and from there I get my rule. And well, here is the nice ASCII print of that rule that we would get here.
These obstructions, sorry, you've got 5 obstructions listed there, gridded.
Right, yeah.
Yeah. Could you say again how you got them?
Yeah, so there's 2 extra ones there. Those are the 2 size 2 ones in cell 1, 1. They're in the background because when you have a point, if I risk going too far back, I went too far back. That was always going to happen. 1 second. I wanted this picture. Here, when I have my point, it's actually represented by avoiding 1, 2, and 2, 1, but containing the permutation 1. That's actually the point. So then when I scroll forward back to our picture.
I see. Okay. Yeah.
We see, yeah, exactly. Now you can see that those on line 6 and 7 are the ones that we're avoiding to get the point, and then the requirement there on line 13 is the one that's forcing it to be a point.
Okay, thank you. Yeah.
Yeah, so yeah, I have that shorthand when drawing these. Okay, so we have this nice, everything here entirely done by computer, so the computer can find the structural description. Very nice. Okay, so I want to go on to talk a little bit about some of the automatic methods that have been used for enumerating permutation classes in the past. So the first one that we're going to look at is called the insertion encoding. So the insertion encoding, it encodes how you build a permutation by repeatedly adding a new largest element. So here I just thought we could do an example because this is very illustrative with an example. Here's how we encode this permutation. So we start with just this diamond, which is called the slot. And the slot acts as a promise that a point is to be added here. So from there, we're going to add the next element, which is going to be the 1 here. And then since there are points both to the left and to the right of the 1, we add a slot both to the left and to the right of the 1. So the next maximum element, that is the 2. So we add the 2 in. And again, since there is a point to the left of the 2, namely we've still got to leave space for the 3 and for the 5 there, there's going to be a slot put to either side. And then we go on and we add the 3, but now note, since there's no points between the 3 and the 2, we don't need to add any further points. It's the leftmost point, so there's no slot to the left of it, so we filled that slot. And then we go on and we add the 4, and now again we see there's no points between the 1 and the 4, so we didn't need to add a slot, but we still needed to leave the slot open for the 6. And then finally, we now just go in and we add the 5, and then we add the 6. So each of these steps, let me say that again. So we call this the evolution of the permutation 3, 2, 5, 1, 4, 6. And each of the steps along the way we call configurations. So at each step we had 4 choices. Either we add the n and a slot either side, just on the right, just on the left, or we don't add any slot at all. So if we just associate a letter with each of these options, then as long as we know which slot we're inserting into, by some subscript, say, then we can write down a word that represents this process of inserting from the diamond up to the permutation that we're looking for. So this word here is what we call the insertion encoding of the permutation. And then for a permutation class, we simply just say that we form a language by just taking the set of all insertion encodings of a permutation class C. Okay. So we then have this really nice theorem from Albert Linton and Ruskuch, which says that a permutation class is regular if and only if it satisfies these conditions. So these has these 3 equivalent conditions. First, that there are most k slots in any evolution. And then the third one here is a particularly nice condition that says the set B contains at least 1 permutation in each of the following classes. And all those classes are really a fancy way of saying the permutations that look like some increasing over increasing, or maybe an increasing over decreasing, or all 4 of those combinations. In particular, that gives me a really nice, easy linear time check for saying whether or not a permutation class has a regular insertion encoding. Okay, and then I've included Vater here as solving this theorem, but actually he came along and did something pretty cool where he not only do we know it's regular, he then gave an algorithm for computing the underlying automata for this regular language, which could then be used to compute the rational generating function for these permutation classes. So one of the reasons I bring this up is because, of course, I want to brag a little bit about our tilings. So while Vater's method is great, if he had had tiling, that would have been even better, because it turns out we can represent each of the configurations as a tiling. So for example, the slot just represents the set of non-empty permutations in a permutation class. So that's just simply a tiling with a requirement there, that blue point, that just tells me that this is a non-empty permutation. If we then consider the case where you filled both sides, when we've inserted this new maximum, it just represents actually placing where is the minimum point in the permutation. And so you just have to consider how the permutations then stretch using our tilings. And so when we filled the slot, we just have a point tiling. If I leave a slot to the right, we simply get this tiling here, this 1 diamond. If I leave a slot to the left, I get this diamond 1. And then finally, if I decide to do a middle placement, I get that I have this diamond 1 diamond, and we have this tiling here. So the reason that tilings are a little bit stronger than the original given algorithm is because of this ability to track the occurrences. In particular, if I give you one of these tilings, that point no longer plays a role in whether or not a permutation on this tiling contains or avoids a pattern. So we can just remove that point freely. Whereas Vater's method relied on a theorem which said that only some points could be removed. So in our world, we'll always be able to remove all of the points, and we'll see those recursions faster and faster. And moreover, his check did require a little bit of pattern containment, whereas here, because of the extra work we do in stretching these obstructions, no pattern containment needs to be done, which is really nice. So it turns out this method is a lot more efficient for finding the same rational generating functions. For example, one researcher, actually I think it was, I'm sure everyone here knows her, Lara, I think it was, she gave a basis to us which was unable to be solved by the Vater's method simply because it contained, I think, 20 size 5 permutations or something ludicrous like this. And she shared it with us, and with our tilings, we were then able to find the rational generating functions in seconds. So it was a huge improvement. It was a big breakthrough, I thought. Okay, so the next automatic method I want to talk about is the inflations of simple
Yeah, I have a
permutations.
quick question.
Yeah,
This
go ahead.
permutation class that you found a rational function was very small. I mean, the sequence was growing small. How big was the sequence, the enumerating sequence?
Oh, that's a very good question. I don't know that off the top of my head. I
So
know
just
that
wanna
uh,
just make a comment. If the permutation class has many restrictions, then it can empirically generate all of them because there are not that many, and then you can actually literally count them. And since you know a priori that there is a rational function, you can just guess it. And since you know a priori that it's a rational function, that's another way of finding it. But it
yeah,
depends how fast they grow, of course.
I agree. That's I do. I find the guess and check stuff very, very impressive, and I think that is a very effective way here. Um, uh, I'm not sure exactly how fast this one grows. I suspect it will probably have a growth rate smaller than 4 would be my guess. It's probably.
Okay, thank you. But it's very interesting.
Okay, so I thought I would talk briefly about the simple permutations. So this was a pretty big research program in permutation patterns. So they rely on this idea of an interval in a permutation. So an interval in a permutation is just a set of consecutive indices which have consecutive values. So in the grid, this just means that we can draw a square box around the points such that there are no points on the intersect the row outside of the box or the columns outside of the box. We then just say a permutation is simple if it has no proper intervals. Okay, so all of the intervals, so no proper intervals, meaning no intervals of size at least 2. The reason this is so interesting is we end up getting this sort of fundamental theorem of arithmetic, but for permutations using simple permutations. So to define that, we need to have this notion of an inflation of a permutation. So here, this permutation I've drawn is actually the inflation of 3142. So the reason that's 3142 is if you look, the boxes are in the same relative order as the permutation 3142. And then inside the first box, I've placed a 213. And inside the second box, I've placed a 21. The third box, a 1. And the fourth box, I've placed this 1, 2, 3. So here I've just taken 3142 and I've inflated each of the points by some permutations. Okay, and so here is my fundamental theorem of arithmetic, but for permutations, which says that every permutation of size at least 2 can be written as the inflation of some unique simple permutation. And in particular, if the simple permutation is of size greater or equal to 4, then this whole inflation is unique. Okay, where for the two smaller simple permutations, which are 1, 2, and 2, 1, we can make it unique in a relatively straightforward way. But we're just going to ignore that detail for now, but it's a relatively straightforward thing. I hope you can take my word for it. Okay, why is that so good? Well, it turns out if you can give me a permutation class which contains finitely many simple permutations, then we know from Albert Atkinson that any finitely based permutation class with finitely many simple permutations has an algebraic generating function. So that inflation or that fundamental theorem essentially gives us a recipe for building the inflations of a simple permutation in a permutation class. And now my ticks picturing started to run out of steam. So here we've gone to some hand-drawn pictures. So here is an example of the inflation of permutations where I'm also saying that I want the inflation of all the permutations that avoid 1, 2, 3. So let's say that again. I want all of the inflations of 3142 that avoid 1, 2, 3. So I've got my 3142 boxes, and then I've stretched the 1, 2, 3 obstruction in all possible ways. And since this is an inflation, I know that each of the boxes contain at least 1 point. So if you stare at these, that then tells me that some of these cells must actually be avoiding 1, 2. So in particular, the inflations simply become, in each of the boxes, we can have some decreasing sequence. So simply this would be counted by x over 1 minus x to the power of 4 for the generating function.
Hey, the color code, red means it's forbidden or it must happen?
Red is forbidden.
Okay, yeah, thanks.
Yeah, exactly. Okay, so this idea, just want to highlight briefly, it can be extended to any permutation class with finitely many simple permutations, and it can turn into a recipe for finding the generating function for such classes. Brignall-Rosicrucian-Vater, they showed that it is decidable if a permutation class has finitely many simple permutations, but then even better news, Bassino, Bouvel, Pirot, and Rosan, they came along and they gave us, for any fixed basis, they gave us a polynomial time algorithm that actually decides if some permutation class has finitely many simple permutations. So that's even better. It's all good and great something being decidable, but without the algorithm, what use is that? It's even better if we have the algorithm, which is what they provided us. And moreover, in this line of work, when Pivotal came along and joined in, they then added an algorithm for the procedure for finding the generating function as well. Okay, and in their method, they use something very similar to the pictures that I've just drawn here. And in fact, they use something, the underlying core idea is these things that they call embedding, which are essentially gridded permutations by a different name. So all of their objects are really just tilings by a different name, but they came first, so maybe they win, really. But in particular, the takeaway there is one could implement their methods using tilings, and so therefore tilings are, I don't know where I'm going with this, but yes, tilings are useful. So I now want to swap focus a little bit from the previous methods and start turning towards a little bit more propaganda about my own work, and so that is namely this combinatorial exploration. So the idea behind combinatorial exploration is we're going to apply our strategies to the combinatorial set of interests, and each time we do that, we'll create a bunch of rules, and then from those rules, we'll pull out the combinatorial sets there, and we'll apply the strategy, and we'll create even more rules, and after some time, we'll have a huge bunch of rules, and that set of rules we will call the universe. And then within this large set of rules, we're then going to search for this combinatorial specification, which is just simply a subset of rules such that every combinatorial set appears exactly once on the left-hand side. Okay, so it turns out there is a fairly efficient algorithm for doing that, so I've just highlighted it here. The details aren't too important. We call it the prune method. It essentially just starts with the entire set of rules and then just removes any row which contains a combinatorial set that's not on the left-hand side of some rule, rinse and repeat until what you'll be left with is the set of all rules which are contained in some specification, and then you can just simply search through that set in a depth-first search manner to pick out your combinatorial specification. That's great, but we want to ensure that any specification we get is actually useful, by which I mean I want to know that it actually will tell me how to count the combinatorial set of interest. And so that's where we had to start developing this theory of productivity, which I'm going to come back to a little bit shortly if time permits. Okay, but we have this nice theorem which essentially says if I have a combinatorial specification spat out by our algorithm, which only uses productive strategies, which means that they satisfy these two notationally heavy conditions, we then have a productive combinatorial specification, meaning that it has a unique solution to the generating function equations. Okay, so that's pretty neat. So we call our implementation of combinatorial exploration with tilings the tilescope algorithm. And as well as unifying earlier methods, one key advantage of the tilescope algorithm is its ability to utilize this growing library of strategies in this simultaneous manner to help build this greater understanding of the structure of the permutation classes. So each of the two automatic methods I showed you before, they are fully deterministic automatic methods. So either it works or it doesn't, whereas our approach is much more exploratory. We can search with both of these ideas simultaneously at the same time. So here I've included in this figure, I've shown like this inclusion table of the automatic methods in the field. In particular, I've shown combinatorial exploration there. In fact, we actually show that that dotted line coming from the finite enumeration schemes can be made solid, but in order to do that, we need to introduce a new strategy, which we call fusion. And we actually, with a little bit more work, you can even have that solid line coming out of the flexible finite enumeration schemes as well, because that is really just a very clever use of the finite enumeration schemes with some clever use of requirements, essentially, where you're saying that in certain areas you must contain certain things. So it's very clever.
Okay. Can I ask something?
Go ahead.
So these enumeration methods, do you consider them as rules in your tile scope algorithm? And also, having a set of rules, how do you generate the proof tree exactly?
Yeah, so in my language, I consider each of these enumeration methods essentially a strategy. And then we apply the strategy to create rules. And so in theory, I can then use any of the strategies from any of the algorithms all simultaneously, and we add some of our own strategies at the same time. And we just end up creating this deliberately bloated set of rules, which within that set of rules, there will be some small subset which happens to tell me how to enumerate the class. So unlike their deterministic methods, we're just deliberately doing way too much and then searching within there to find the answer.
I see, but is it like a brute force search or no?
At the moment, it's done by a lot of heuristics, but it's essentially this sort of breadth first type algorithm where we apply the rules to the root, and then we apply it to all of its children, and then we apply it to all of the children, and so on. And we just slowly create this bigger and bigger universe of rules. We have some heuristics to try and get through that in a helpful way, but nothing more clever than breadth first, really. So yeah,
Thank you.
it's quite experimental and exploratory in nature. Okay. So yeah, as I said, we apply these strategies, we create a universe of rules. So now I'm going to try to talk a little bit about that productivity stuff that I mentioned. So we're going to search for specification within this universe. So first of all, what is a specification? Well, we already said it's a set of rows where each class appears exactly once on the left-hand side. And then what is a row? Well, to define rows, we first need to define strategies. Okay, so we're going to let X be the set of combinatorial sets. Then we define a strategy as the following. It's really just this triple, where the first thing is a decomposition function, which tells me how I can decompose my combinatorial set into some collection of combinatorial sets. Okay, so we have this X going to XM here. And we'll write, for example, DSA here to mean that I've decomposed the combinatorial set into the sets B1 up to Bm here. And we have this does not apply thing just in case for details that aren't that important, but just to say that the strategy doesn't apply, right? We then have this thing called a reliance profile function, this is where we're heading towards the admissible constructors. So in Flageolet and Sedgwick, they define these things called admissible constructors, and they give sort of 6 examples of admissible constructors. But unfortunately, when you then come to try to implement Flageolet and Sedgwick, you say, well, I need you to be more precise as to what you mean by an admissible constructor. And so this is where our notion of reliance profile function comes into play, as we're just trying to sort of formalize those ideas that were always sort of intuitively taken for granted in some of those works. Okay, so this reliance profile function is going to dictate what sizes of the combinatorial sets so what size of the elements from the combinatorial sets do you need to know the counts of in order to count the combinatorial set you're trying to count from? Try that again. It's going to dictate the sizes of the elements from the combinatorial sets from the children in order to count the parent. Okay, this will be better with an example that's coming on the next slide. And then the third element to my strategy is simply going to be a counting function. So notice that the counting function doesn't change, it's stuck with the strategy. So the strategy and the counting function are heavily linked. And so the counting function then just tells me how do I actually go about counting the parent where you're only allowed to know the sizes of the sets for the children. Okay. And you're only allowed to know up to whatever that reliance profile function set. So let's be more specific. So if we consider the really simple strategy, which says that your combinatorial set is either your element is size 0 or your element is not size 0. Okay, so we'll call this the strategy Z here. Well, then when we decompose some combinatorial set A, it always has two children. We have the set B, which has precisely the element of size 0, and the set C, which has everything that is not size 0. Okay, so A is actually the disjoint union of B and C. Well, if I wanted to count the parent set here, where now I know it's a disjoint union, then I'll need to know, if I want to know how many size n objects there are in A, I will need to know how many size n objects there are in B, and how many size n objects there are in C. And, well, now what is the counting formula for that? Well, it's simply, well, it's B. If Bn is the number of size n objects in B, and Cn is the number of size n objects in C, it's simply Bn plus Cn. So here in my counting function, you'll notice I've given it a lot of extra inputs here because we've got B0 up to Bn and C0 up to Cn, but that's just sort of a quirk of the way we set this up, and that will be useful when we think of our second strategy, this idea of Cartesian product. So in our example for AV132, we also needed this idea of factoring around the maximum element. So we will say then that this particular strategy will say that A decomposes into BC if I can write A as that picture that we had on the previous slide where we had the maximum element and then the B and the C were separated out. Okay. Now, if I want to count that, then in order to count that, I need to know how many objects are there in B of size up to size n-1, and I also need to know that up to size n-1 in C. And why is that? Well, that's because I can then use our convolution formula, and we see then that to count the parent, I need to sum up j equals 0 up to n-1. We have this bj cn minus j. So the reliance profile function is telling me that I only needed b0 up to bn-1 in order to count this class. Okay. So yeah, just some notation. We will then say a combinatorial row. As a shorthand, we'll write it as A goes to B1 up to Bm, and we'll have S on the arrow here. Okay. Well then, a specification is just simply a set of rows where each combinatorial set appears exactly once on the left-hand side. And we now want to define exactly what we want is a productive specification, namely the ones in which we can actually find the unique solution given the counting function. So a specification with k rows we say is productive if the counting functions have a unique solution in this set here. Okay, well, it turns out we can actually describe a case where we can describe quite clearly when a specification is actually productive. And to do that, we need to define this infinite directed graph for a specification. So for each combinatorial set, we define an infinite set of vertices. So that is just going to be one vertex for each combinatorial set and the size here. So if you've got the combinatorial set A, we'll have one vertex for the size 0 objects, one vertex for the size 1 objects, and so on. And then we'll have a directed edge going from one vertex to another vertex if, first of all, they appear on the right-hand side of some row with the left-hand side. So if there's like a row pointing from one to the other, And then moreover, this number of objects of size I1 relies on the number of objects of size I2 in the other combinatorial set. So we have this sort of infinite directed graph. Then any proof tree or combinatorial specification involving these combinatorial sets whose reliance graph contains no infinite directed walks, it turns out that will be precisely a productive specification. So in other words, a specification is productive if its reliance graph contains no infinite walks. Okay, so this is our way of checking. So if I be really concrete again, I go back to my permutation class AV132. This is our specification written up a little bit more formally using this notation of strategies. So we have these three strategies, S1, S2, and S3, which broke it up, where S1 is just saying either I'm the empty permutation or not. S2 is saying I can factor around the maximum element, and then S3 is actually the strategy which is pointing to a tuple. Why? Because S3 represents the empty permutation, and we just know how to count that. That is 1 of size 0. And it has these reliance profiles functions, and if we were to draw a segment of the infinite directed graph, well, now we know, for example, that for A2 here, we know that A2 now relies on A1, but it's always relying on 1 down. So A1 goes to A0. I'm getting my words all mixed up here. Yeah, so A2, yeah, it's relying on A1, but each time it's only relying on the objects of size 0 through n-1. So we have all of these arrows sort of pointing to the left rather than to the right. And in particular, you can actually then partition this infinite directed graph into these segments. And if you stare at it, you'll notice that there's no edge that will go from some Sn to some Sn plus 1. And so we have no infinite walks and we have a productive specification. Okay, so that was a bit of a whirlwind tour of that theory. And we then defined this idea of productive strategy as before, and we just have our theorem that says if my combinatorial specification is made entirely of productive strategies, then it is in fact a productive specification. Okay, however, it turns out that there are actually productive specifications with rules from strategies that are not productive. But that is a story for another day, as I'm starting to run out of time. And that was actually an entire PhD thesis from Emile Nadeau, who was one of the authors listed at the top. So to summarize, currently combinatorial exploration exists as this rather long paper on the archive, but soon it will appear in the memoirs of the AMS. So the idea is it just gives this automatic method for rigorously studying the structure of combinatorial sets, direct from problem statement rather than description. And it allows us to count these sets, and in many cases also actually sample uniformly from these sets, something I haven't really talked too much about today. Along the way, we need to strengthen the foundations of combinatorial specifications, but what I mean by that is essentially give a computer-precise definition of what was meant by admissible in the work of Fleischerle and Sedgwick. That being said, that being precisely that productive stuff we talked about briefly and sort of had this crash course in at the end of the seminar there. We then applied the framework extensively to permutation pattern problems, and I showed today how it unifies previous earlier automatic methods, as well as adding a lot more. It is then able to rederive hundreds of, if not more, results from the literature in a unified manner, as well as proving many, many more. We share our results on our database or on our website, permpal.com. And so here on the right-hand side, this is a screenshot from that website. Included on there is actually all of the 2x4s, this, by which I mean all of the permutation classes avoiding 2 permutations of size 4. So this actually was a pretty big deal for our field. Over the last few decades, there has been a really strong effort to enumerate all of the 2x4 permutation classes, and often it would take an entire article to enumerate every single one of these. Our framework was actually able to enumerate all 56 of them. In particular, we were able to then sample uniformly from our specifications, and we were able to create these heat maps here. So here we have some heat maps for these classes, where what we've done is we've sampled 1,000,000 permutations of size 300 and then overlaid them so the dark regions sort of correspond to where points generally are and the light regions where they generally aren't. So we get this really pretty picture giving this sort of idea of the structure of these classes. I also like to point out at this point that this really was a pretty mammoth effort and lots of people have been involved. So here is a list of some of the many students who have also helped throughout encoding efforts to make this all possible. Okay, so I guess in the other directions, well, I briefly mentioned specifications with non-productive strategies. We call these things.
Sorry to interrupt, Stoyan. I think its time is up. So,
okay.
Yes.
If you will allow me to put this slide up then at least.
Okay.
Okay. Some advertisement, permutation patterns. So let's thank our speaker. And yeah, the floor is open for questions.
I have a question. You had that slide with a sequence on it. You didn't give the OAIS number for the sequence. That would be helpful, right? Yeah, that one.
Actually, if you look on our webpage, we have search on the OAIS there, because I agree that was exceptionally helpful. We love the OAIS.
Yeah, I just didn't see an A number there. I was expecting to see something that would say.
We just have a button there that allows it that will automatically search it on the OAIS.
I see it. Okay.
I know, but this is a sample of your website.
Yeah, that's right.
How it looks, a typical page.
Right, exactly. That's exactly what a typical page looks.
So Neil is right. It is no mention of the word OAIS in the whole page.
No,
actually
there is.
So it should be. Okay. I hope you're going to fix it next version.
Yeah, so just under the counting sequence, you can actually see there is a button, a clickable button that will then take you to the OAIS immediately.
Oh, if you click it, yeah.
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 It'll take you there on the fly. What does it do? It looks it up and reports back what it sees in the OAIS?
Exactly, yeah.
It's a single sequence, so either it's there or it's not. You could give the A number.
Yeah, that's true. We have actually got in our database thousands of sequences, and we've been thinking about the best way of getting them onto the OAIS for a while. Yeah.
Good. Yeah. I could help with that if you need help. Yes.
Yeah.
That would be worth doing.
Yeah, definitely. We have so many, and we'll just keep getting more and more because now we have this automatic system for finding them.
Yeah, good.
Can you apply these techniques to other objects besides permutations? For example, Latin squares or Latin rectangles at least.
So we haven't done it to Latin squares specifically.
Latin square would be too hard, but Latin rectangles with a fixed height.
I haven't thought about that object specifically. I have a feeling it's going to be quite hard. Objects that we have had success with would be currently we're working on something that we call Keele permutations. So these are just ordered set partitions. We've also had some success working with some lattice path enumeration, so like Motzkin paths and Dick paths, etc. And in our paper, we gave an example for finding a combinatorial specification for a class of polyominoes, which is kind of cool, but that's going to be a pretty big endeavor for in terms of the code. We've also had some people, we had a group in Canada that were working on matchings, and they used our framework for that. And I'm also working on some projects on inversion sequences, and we're using our framework for these things. And so yeah, we've got
nice.
Yeah, it's very applicable actually. Here I really focused on the permutation patterns because that's where it started, but the whole idea was that combinatorial exploration should be domain agnostic, and then you can go in and you can just put your own domain on top.
There's one direction it would be very nice to go, is infinite permutations. Have you thought about that at all?
Wow, the word infinite doesn't sound very good for my computer.
Well, you'd have to work harder, yes.
Yeah. I'm gonna need to think a lot about that one. I haven't actually thought about it. I've seen some definitions of infinite permutations, but that
Or
could be
have you
fun.
been able to get applications to some of the standard kinds of graph theory enumeration problems of different kinds that people have looked at over the years?
Yeah, so we had we did think a little bit about graphs in this world, and they're also quite difficult to get a handle on. So we had some very basic specifications drawn at one point for some labeled graphs. I think we kind of needed the labels to get started. Um, but yeah, I'm not sure where I'm going with that. But yeah, I think graphs would be great. I really need some graph theory expert to come in and just take the reins at some point.
I can suggest problems, but I
Yeah.
can't provide any useful insight in how to solve them in your context, or in more classical context.
Okay, yeah, that's fair. I did see one paper where they were using combinatorial specifications to enumerate graphs, so I should probably look closer at that.
Okay, great. Maybe one last question from me would be, do you have some conjectures listed in the website? Maybe some people got conjectures.
Okay. So one thing that I haven't really had a chance to touch on is sometimes our algorithm will return essentially a polynomial time algorithm for counting the class. So in which case we can often get hundreds, if not thousands of terms. But the system of equations that it implies will have maybe 2, 3, or 4, maybe more catalytic variables. And so we don't actually have tools for solving those systems of equations. So we know a lot about the permutation class and its counting sequence, but we don't have a generating function for it. So you can kind of just search on the website and just say, does it not have a generating function? And there's a challenge for you. Can you find the generating function? We actually, that might be a very difficult challenge because we do have some counting sequences on there for which we know the permutation class has a non-algebraic generating function. So don't expect these all to be easy questions.
Okay. Are there any other questions for Christian? If not, thanks again, everyone, for coming. Christian, please send us the slides, and the recording will be uploaded as well soon.
Thank you, Christian. Very interesting. So
Yeah, thanks, everyone.
Yeah,
Thank
very
you.
nice talk. Yeah, thanks. Okay, bye-bye, everyone.
Thank you.
Bye.